Let's do a lecture on graphs. First, a homework from yesterday. There is a graph. You start somewhere. This is the start. Their edges, they can be directed, but they don't need to be. And there is some target. This is the target. And every turn, you start here, every turn you're presented with one random edge among edges that go out of the current node, and you can use it or not. If you don't use it, then you wait for the next turn, and again you're presented with a random edge. Here I would say that if we are given this edge, then we use it. If we are given this edge, then certainly we don't want to use it. And if we are given this edge, this one, we don't care, we can accept it or not, whatever. We could make, of course, this more complicated, where this would be a path, this would also be a path, and depending on some, comparisons of distances here and there, maybe you want to use this edge or not. Maybe there are multiple edges that you would accept starting from here. Your strategy, basically, is at every node, for any edge that is presented to you, the decision whether you would use it or not. You need to minimize the time to get to the target. So find and minimize the expected value of number of turns to get to the target. That's what we need to compute. It is a real value, not necessarily an integer. We already talked that yesterday in the version without cycles, that if you are somewhere and there are two edges that you would accept with some scores here already computed, let's say 20 and 35.5, and there are, let's say, 3 more edges that you wouldn't accept. If you're presented with those choices, with those edges, you would wait because you want to wait for those. Then what's a way to compute the answer here? You have probability of success 2/5 to be presented an edge that goes to something that you accept. This means that on average 1/p is 5/2. This is on average how much you wait while you keep getting red edges, those that you are not happy with. And after that many on average, you will get one of those two with the same probability. So this is a way to compute a value that needs to be put here as the question mark. But we cannot decide anything looking at this node because we don't know values for those values. This value 20 is starting from here. What is the expected value of how many turns there will be before I get to the target? We can only initially say that the answer here is 0 in the target, everywhere else is infinity, and for neighbors of target we can start doing something. It turns out that the way we should apply it is basically Dijkstra backwards from the target. Dijkstra algorithm, where for each of the neighbors of the target I can put there some possible score. Like here, in this node, it can, when you are here, possibly you will accept an edge to the target. This is one of 3 edges, so on average you will need to wait 3. For every neighbor of yours you can do that. This will be 4 and this will be 2. Those are possible values. Maybe I need to improve them. For example, in a moment, let's look at this guy, this node. Maybe instead of just accepting a node towards the target directly, an edge towards the target, it should also accept this one. So let's look closer. I will zoom in. If you're here in a node, I will call it A. If you're presented an edge to the target, of course you accept. Sure. But what if you get an edge here to a node with value 2 written there? Well, you can again use some formula. If you accept 2 out of 4 edges, then on average you will wait 4/2, plus you will get to one of those 2, 0 plus 2 divided by 2, that's in total 3.0, so it's better. I'm improving this from 4 to a 3.0. Again, it disappeared. I don't understand why. 3.0. Then you could also compute whether from here it's optimal to accept an edge there, but it will turn out, I believe, that it doesn't matter. When should we update this edge? When we see that there is a neighbor that is better, kind of, and the exact behavior is this. At any point, let's see the current situation now. When you see those values, 4, 3, 0, and 2, 0 is already considered, you can almost forget it. But is it now smart to look at this node and compute the answer here? From here, what is the expected number of steps until the target? No, because neighbors aren't computed yet, and we might still need to update neighbors. Maybe 3 and 4, and this one will be improved. Just like in Dijkstra, after you're done with 0, you should take the lowest value, here it's 2, and then you know this value 2, when I get to it, it's for sure correct, and I will never modify it. 0 is certain, it's for sure 0, 2 is for sure 2. Now we iterate neighbors of this node, and we update their scores. Here we would update 4 into 3. And then again, those 2 are done. Now for those, any one of them you can take. So always take the smallest value, like in Dijkstra, that you haven't processed yet, and then update all your neighbors. To all your neighbors, tell them, hey, I have this value, 3, and maybe you are happy going into me with value 3. So for this neighbor, just update its score. For example, if there is here, I see a value, I see a node with value 10.0, and this is the lowest value not considered yet. There are here some other nodes that are neighbors to my neighbor. Let's say that here is 7.5, here is 13.0, and there is here infinity, because initially everything is equal to infinity. Okay, now let's say that this one was already considered. I don't need to look at it anymore. And right now this is the best. Also, this node has value, say, 27.77 there. We run Dijkstra starting from the target. We already processed this node. There can be some other nodes in this graph, but now we look at this one. We iterate its neighbors. 7.5 we can skip because it's smaller than me. But 27.77 we should update. So 27.77 already saw this small neighbor, but now it gets one more nice edge to 10. So I minimize 27.77, I minimize into 4 divided by 2 plus 10 plus 7.5 divided by 2. Whatever the value is, it will be lower, so I just put it here. So this is the value there. And I don't right now consider other neighbors of mine, like 13.0, because it's not updated yet. Maybe this one will decrease. Later on, let's say that it turns out the next lowest value, after we are done considering 10, the next lowest is 13. If so, sorry, I'm just checking something. Yeah, if so, then we will go through all neighbors of 13, including this one on the left, and we will update its formula, possibly updating the score here in green. Maybe right now this says what, like 8.8 plus 2, 10.8 or something. Now this 13 should tell this node, hey, you have a new possible formula. You can update this formula by saying plus 13, divide by 3, and here divide by 3. You can observe from what I'm doing that updating this formula isn't that complicated and it can be done fast. So I want to get time complexity equal to Dijkstra, so just O of n plus m multiplied by logarithm of something, as always in Dijkstra. And for that, when you look at any node and you update its neighbors, you want to do it in constant time. So you want to compute this formula in constant time. This formula says my degree divided by the number of smaller neighbors plus the sum of smaller neighbors divided by count of smaller neighbors. And oops, this shouldn't be 3, it should be 1. I think that this is degree minus smaller, because this is actually how many are bigger, how many you don't accept. This formula, it was the inverse of P. P is bad neighbors divided by all. Then inverse of that is all divided by bad. Yeah, so it will be like this. And for that, for every node, you should just maintain those variables. So store in node, or for every node you need to know its degree, and that's integer. Sum of smaller neighbors, or small neighbors. What else? Count small neighbors. You need to store those 3 things in a node. If you do that, when you get in Dijkstra to any node, go through all neighbors, and if something isn't processed yet, isn't smaller, so you skip it, then you increase this value by 1. Sum of small neighbors you increase by the sum of this neighbor, and you update the answer, well, the main thing, or the distance. I can call it distance, maybe that will be easier. Distance from the target, kind of, and I minimize that with formula that I can compute in constant time using those values. If the distance indeed improves, I update it in priority queue /set in Dijkstra. The end. Any questions? I'm waiting because somebody is typing. Next will be CSES swap game. I will open it already. Shouldn't 10.82 be processed before? Oh yeah. It's not that I actually processed this in good order. If already here is 10.8, then it would be considered before 13. So let's say that what I wanted to say is, if this turns out to be the next smallest, let's say it's 10.5, then it is before 10.8. So this one will possibly update 10.8 into something even smaller. And generally, whenever a value is smaller than the value in a neighbor, it will update it, because you're happy accepting this possibly, and this will be slightly lower. Thank you for noticing. Okay. 2, swap game. Swap game is an easy task if you know this kind of tasks, basically. And you have a hint right now that it's a graph problem. We are given a 3x3 grid, or a game, where there is some kind of move allowed, swapping 2 neighbors, and we need to sort the grid. You can try some greedy solutions here, but I think they will not work. Maybe if you do enough work, they will work. But always, this is the current grid, let's say. And you can do different moves, like from this you can make a copy, and let's say 4 can be swapped with 2. That's one example. I swapped those 2. But also I can swap, what else can I swap? 2 with 7. Like that. And there are many more moves that I can make. And because I want to get some particular target grid, the solution here is to run BFS in this graph. BFS in graph of states. This is a state, this thing. So you can think that this is a node. If you want, you can give it some ID. So maybe in your code, this thing will have ID 0. This thing maybe will have ID 77. This thing will have ID 80, and so on. And you want to find the shortest path from node 0 to some other node, representing a grid 1, 2, 3, 4, 5, 6, 7, 8, 9. And I want to talk about implementation and how to think about that. You have two choices, you have choice 1 is you can choose between storing graph explicitly, or you can traverse edges as you go. This is the first choice. Second choice is that you can represent node as vector or 2D vector, or you can represent compress into ID, into integer ID. Those two choices are almost independent. And maybe for some of you this is trivial. Well, that's fine, you will be bored for a moment. But there are multiple ways to implement that. And I want you to know about those ways. How can we implement this search for what we can do, what kind of movements we do? First thing is that we can create a whole graph and store it with edges. Let's first talk about code that will combine this thing with this thing. But I think any 4 combinations are okay. What is a node? A node is an array of size 3 by 3. Or if you want, it can be a 2-dimensional vector. So maybe you want to use one of those. And let's do something that is, I would say, middle ground. Let's say that I have a vector of size 9. Right? So this thing will be represented by an array 1, 5, 3, 2, 4, 6, 7, 9, 8. So this will be my vector. I will say 1D or 2D. And how do I store the graph explicitly? For every possible vector, for every permutation, I can create all the edges, which is tricky. It requires some work, but I can do this. So pre-processing. Create full graph. How do we do it? For every permutation of numbers 1 through 9, you need to iterate all possible states. You can do that by using function next permutation. In C++, next permutation is very useful for that. For every permutation, map it into 2D array if you want, but it's an optional step. And then consider all moves from the statement and keep doing something like this. Edges of my current permutation, pushback, new permutation. Do this for every possible move. Now, what is edges? This would be in this case a map from one state to a list of other states. Edges. Or I will maybe make it easier to read. State. State. This is a general recipe for what you can do, or how we can store edges in a graph. If something is a current node or state, from this node there are edges to a vector of nodes. You can have a map for that. Right now my state is a vector, but it could be something else. And when we have a permutation, I need to iterate all possibilities for what I do with that permutation, what the statement allowed me to do, like swap two neighbors in 2D. And I see some new permutation. I say, okay, from this to this new permutation I can move. Then once I do all of that, then just run BFS from starting state. read from input. Preprocessing can be done without reading the input. Then you read the input and run BFS. That's solution number one. It's a combination of creating a graph to store it explicitly in a map and representing every node as a vector. This combination uses a lot of memory. I will say this, that about this combo, that it is maybe easy to debug because we literally do what the problem statement does and we can print what kind of edges we have, but also it uses a lot of memory and the time complexity isn't great. There is big constant factor, so I will just say generally slow. Whether implementation is convenient or not, I don't know. It's similar to other options. And now what else we can do? Traverse edges as you go. To save memory, and because of that also time, we don't actually need to store edges. If you want to run BFS in a graph, then you can just, when you get to some node, you can then consider all possible moves and see if those new states are not visited. So a moment ago, what we had is create and store graph, read input, run BFS. That was version 1. Version 1. Now I say that there is version 2, and often it's better, and that's just read input, run BFS, inside iterate edges each time inside of BFS. What I mean here is inside of BFS while loop, or however you implement BFS with a queue, when you have some current node, current state, then you can, whatever you would in version 1 implement here to push back those edges, here you don't store them anywhere. You just say, okay, if I have state 1, 2, 3, 5, 4, 6, 7, 9, 8, in particular I can swap 1 and 2, and you make a for loop to consider all those states, all those swaps. So maybe this is the new state, and I just say, if this thing is not visited yet, then I push it to the queue and I mark its distance as my distance plus 1, like you always do in BFS. Okay, so that's version 2. I would say then that assuming that you will traverse your graph only once, then this thing, instead of storing edges, is better memory for sure. Almost, sometimes actually it's almost zero memory. So low memory. And it's useful mainly if you want to traverse once, one traversal. Because if you want to run some BFSs multiple times, then it's most likely faster to just iterate something that is already stored and found, instead of trying to create it from scratch, especially if rules of the game are more complicated. Okay, what about this second choice? Instead of having a vector of numbers, you can make everything more compressed, and you can just say, for example, that 1, 2, 3, 4, 5, 6, 7, 8, 9, this is value 0 or node 0. Then maybe 1, 2, 3, 4, 5, 6, 7, 9, 8 is value 1, and so on. You can, every permutation can be mapped into a number from 0 to 9 factorial minus 1. And there are different ways to approach it. You can create a map. You can create a map from vector to int. That's one possibility. You can also try to, given a sequence, you can try to figure out it is what ID of lexicographically smallest sequence. Like this is, for example, the second lexicographically smallest permutation of numbers 1 through 9. And the way to get such ID is basically to go through numbers, and always when you see a number that could be smaller, increase the ID by something factorial, because something happens with a suffix. We are here basically solving a problem. Given a permutation, count lexicographically smaller permutations of it. This is solvable. The fastest way to do it is with a segment tree, but we have such a small sequence that it's not worth it. So just make it quadratic. And this way you will be able to map it like that. And then you can work with numbers from 0 to 9 factorial. And if you, for example, want to store the full graph, it will be way faster to do it. So I would say that this thing is a good combination with storing graph. I will say that this is good combo. Because if you want to store a graph and then run BFS, DFS multiple times, maybe you will get queries. Maybe multiple times you will have some starting grid, target grid, and you need to run BFS again. Then instead of bothering with long vectors, maps, you just want to have a normal graph with IDs counting from 0 and run normal BFS. That will be fastest. Does it make sense to traverse edges as you go and compress into integer ID? I think that this one is a bad combo, bad combination, because every time when you look at some integer ID, like you have a permutation with ID 70, you need to, I think, change it back to a permutation to know what kind of swaps are available and then change it back to ID. So this seems to be a lot of work. So I wouldn't recommend it. I think other than this combination, all other three options are fine. But this one, I don't see how you would do this. After the lecture, you can, if you want, solve the swap game in CSES in at least 2 ways. So maybe try combining those two, and also try combining those two. If we use something like polynomial hash for the ID, the thing is that what we did here is also hashing. It's just perfect hashing. But the question is, if you use polynomial hashing, then if you ever see ID, like you see ID is equal to 70, are you able to traverse edges? If you stored it in advance, then yes. So you can use polynomial hashing to, given a grid, turn it into ID. But what you cannot do is turn ID into a grid, or at least it will be very, very difficult. Unless you have a map for that, or a vector of vectors. But then again, you have high memory. So most likely, if you want to use polynomial hashing to change grid into some value, then it means that from some moment you want to only use IDs, and it might be fine. For permutations, it was easy, quite easy to turn it into IDs in a unique way, so that there would be no collisions. For something more complicated, like the same problem for a sequence, so you're given 3x3 grid with arbitrary values, and you need to turn it into a new order of it, then yes, I would use polynomial hashing, I think. Okay, second is done. Third task. There is an elevator with 3 buttons. You start from 0 and you can move up by A or B or C. They are all positive. How many different floors up to 10 to 18 can you reach? Or similar version of this problem would be how many floors up to A times B times C can you reach? Of course, elevators could be dropped from the problem statement. We could talk about a counter. You have a counter initially set to 0, you can increase it by ABC. Now, I see that I'm not happy with the constraints here. I think the better constraints go like that. A times B times C is up to 10 to 18. If the problem statement said that, then you need to figure out yourself that it actually implies that one of them is up to million. So I would say ignore this and let's say that this was the constraint, which is possibly more difficult to solve. Okay. How do we solve it? There is some kind of cycles here. So this is 3 elevators. Oh, I can just copy the statement, right? Okay. Let's say that A is equal to 5, B is 2, C is 3. Maybe bad example. 7, C is 8. This might be better. If any floor K is reachable, then also K plus A is reachable. So for every remainder modulo A, there will be some first floor that you will reach. Maybe, let's say, you are able to reach 7. So because of that, you reach 12, 17, and so on, and you don't need to investigate those. 7 is the smallest floor reachable with value 2 modulo 5. So idea is for every remainder 0 to A minus 1 modulo A, find the first such floor reachable. Now, because we do this, we can now ignore moving up by plus A, because by doing this we already do it. And here's what I will do. For 0, initially I set it to 0. For 1, it's infinity. 2, it's infinity. 3, it's infinity. 4 is infinity. This is the initial answer to this task that we're solving. And then, when I see a 0, I consider those two moves. From 0 plus 7, I can get 7. So that's value 2 modulo 5. So I put it here. And I can move by plus 8. I put it here. Then from 7, I can move by plus 7. I will get 14. 14 modulo 5 is 4, so I put it here. Or 7 plus 8 is 15. 15 modulo 5 is 0, and this doesn't improve the situation. Then this plus 7 is 15, so skip. Plus 8, it's 16, put it here. It is possible that somewhere value will be big and then we improve it, because we see, oh, actually this better solution exists. Sometimes it may happen, but generally we are here running some graph algorithm. I can even draw the full graph. We have nodes 0, 1, 2, 3, 4. From 0 you can get to remainder 2 by using value 7, and here you can use 8. From 2 you can move by plus 7, you will get 9, so you will get here. You will also move there with value 8, and so on. So you put 2 edges from every node. I'm using different colors just for clarity of the picture. And this one, no, this one and this one. Okay. All edges have cost 7 or 8. And I claim that I need to find shortest paths from 0 to everything else. Because we have costs, the algorithm for this is Dijkstra. So we just run Dijkstra again, starting from node 0. This way, I will know for free what is the smallest cost of getting from 0 to something that has remainder 3 modulo 5. And if the answer here is 8, then it means 8 is reachable, but also 13, 18, 23, and so on. So what's the solution to the problem? Get the minimum among values a, b, c for the speed. But here you can just take a, whatever. Create a graph. Again, you can do it explicitly or not. You can store all edges. So the first part of your code can be this. Vector of vectors for edges of size A. For every value, for every remainder, consider moving by B or by C. And from I you will move to I plus B modulo A. Right? So you need to say edges, pushback, an edge towards I plus B modulo A. You also need to include the length. So actually you will have here pairs, and every edge will be information to what node it leads and what is the cost. That's an edge. Then run Dijkstra from node 0. Then for everything here, you look at distance of I, and this will tell you for this remainder what is the first reachable thing. And you know that you need to count floors up to n that are reachable, so you will do something like answer plus equal n minus distance divided by a. Ceiling of that. Right? If from 14 you need to count floors up to 100 that are divisible by 4, it will be something like this formula, maybe +1 somewhere. This is solution number 1. Time complexity is n log n, or a log a. The graph size is a, but you run Dijkstra. And you don't need to actually explicitly store edges. You also can get rid of all of that. And when you run Dijkstra, you start from node 0. This is the only thing that has distance set to 0. When you have a node, just consider both of those possible moves by plus b and plus c, and see if this new node has, like, if you would improve its distance. If so, you update it and put in priority queue or set. So this thing can be inside of Dijkstra if you prefer it that way. Okay, questions? And here I used those constraints because if you see that the product of few values is up to something, it usually just implies that the smallest value is smaller than square root, or here cubic root. So if you see that product of 3 values is up to 10 to 18th, it means minimum of those 3 is up to 1 million. Time for questions if you have any. Then let's talk about DFS tree. I will tell you a few random things, maybe you will learn something new. And I will also show you this. I will give you a link to this. Maybe I will paste now in the chat. DFS tree blog. It's a nice blog by Is This FFT in Codeforces. But you should understand everything from it if you want to perform well in IOI, I would say. First thing is this. When you have an arbitrary graph and you run DFS in a graph, then you need to understand what that implies. Let's say we have something like that. You run DFS from here, DFS. This is the starting node. How DFS can behave? Let's say that it will go like this. Then it will visit this neighbor. Then because there are no other neighbors of this guy, it will go back. Then it will visit, let's say, this neighbor. This one. Something is wrong with my software. This one, and then it will go back, because there are no other neighbors. From this one, still it will consider, let's say, this guy and this guy in some order. Okay, so what we got is, let's call this A, this one B, C, D, E, and the others will be unnamed. We got a tree that looks like that: A, D, then there was B, then few unnamed, there was a long path here, then we had E and C. E, C. Okay. Let's now focus on this tree that we got. This is called a DFS tree, and it's not unique. For the same graph we can have many different DFS trees depending on the order how we visit neighbors of something. And DFS tree has size n-1, obviously, but there are extra edges. 1, 2, and 3. Edges between AB, AC. So this is the edge, and this is the edge. And also edge between unnamed and D. So this is the edge. Like that. Now, those red edges, those back edges, we have back edge. I will mark it in red because this is the color here. And we also have spanning edges. This one is just normal, or green. I should make it green. So this is a spanning edge, and this is a back edge. Why do we call it a back edge? Because when you look at this drawing, then D was visited first before everything here on the right. And when you have this neighbor of D, it tried to go back from this neighbor to D in DFS, but it saw that its neighbor is already visited. It tried to go back, but couldn't. Here in the tree, it looks like this. From D, we traversed down, 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 and this one saw that it has a neighbor that is somewhere else, but it was already visited, so it skipped. The most basic and important thing about back edges is that there cannot be an edge like this. This doesn't exist no matter how you run DFS. This red thing is not a back edge. Why? Because when you are in D and you will go first to one of neighbors, either this unnamed child or to C, when you go there, you will keep traversing in this subtree, and when you are in this neighbor, then you would go to C because it's not visited yet. Yeah, exactly like somebody in the chat said a moment ago. So instead, C would be connected here. It would be green. It would be part of DFS tree here, and that's it. So back edges only go up. They only connect, we say, descendant ancestor. It's like child and parent, but they can be far away. One can be grandparent of the other. And it implies a lot of things. For example, every back edge gives you a cycle, right? This is a cycle. No back edges means no cycles. If there is one back edge only, it is one cycle. Also, in some very difficult parts, you need to use this fact that every cycle is a combination of basic back edge cycles. I hope that I'm not saying something stupid now, but in particular I claim this. Let's say that there are 5 back edges. So 5 red, or here we have 3, right? We have 3. Then I claim there are at most 2 at power 3, which is 8 cycles in total in this graph, including some repetitions. Why is that? Well, we have a cycle here we have a cycle here, we have a cycle here, but also we can use some things multiple times, and sometimes it will lead to a stupid situation where you're using edges multiple times, but like some edges might cancel out. So a cycle might be combining this cycle with this one, right? And this is one big cycle because I can traverse it like that. Now, actually, you can argue that here, even when you enter a cycle, you have two ways of traversing it, this way or this way. But let's say that it's still the same cycle. This, what we see on the screen right now in yellow, is one cycle. We can also combine this thing with this one. If you don't want to visit the same edge multiple times, then it just cancels out. If one edge is twice in both cycles, then it's actually not in the combination. So from that, it's this. This is another cycle. Every subset of back edges gives you a possible cycle. And now it's tricky how we define cycles. If the order is important, then actually, so if order in cycle is important, then more. But basically, you have a tree, you have some set of back edges. Some can be like subsets of the others, that's possible. And once you focus on some subset of them, let's say those three, then they, together with their normal edges there, that can be combined. And now if they are far away, then it's actually impossible. But if they intersect in some way, like maybe say that this was one back edge and this was the other, then the back edges, they combined something that happens in parallel. And there should be now a way to traverse. Is there a cycle here using those two back edges? Yes, there is. No, I'm using this twice. Yeah, I'm using green, red, green, green, red. Oh yeah, the whole drawing now right now is a cycle. Just all those edges, if you traverse them in some proper way, is a cycle. Okay, but now this was maybe an interesting fact, but I don't have a particular task to show you. Still, I will show you some other properties of what is going on here. For sure, many of you know that this will easily give you not back edges, bridges and articulation points. Why is that? Because back edges are the only thing that will give you cycles, and everything that is part of a cycle is not a bridge. Bridge means something that disconnects a graph, that you don't have any other way to traverse. So, is this edge a bridge? Is this a bridge? Question mark. No, it isn't, because there is a red edge that is an alternative to it. So the question is, to check if this is a bridge, the subtree here, does it have at least one edge that is red and goes up above this thing? And there are multiple ways to check that. You can run the FS, but if you want to be efficient, one way is this. Among red edges, back edges in this subtree, find the one that ends highest. So here, find the one going highest. And this is the main algorithm that people use to find bridges. You can use dynamic programming to know for every node how high a back edge goes. Like here, it goes here to D. So, and for every node, you can compute depth. Let's say for root, the depth is 0, then this is 1, 2, 2, 2, 2, 2, 3, and so on. Then also for every node, you can use dynamic programming to compute first, without DP, what is the depth just see the depth of the back edge. And then in every subtree, I want to know among different red edges here, what is the one that goes highest? And then we will check if it is higher than this level. You can check articulation points in a similar way. What else can we do? I can just, let's say, count endpoints or something like that. When you see a back edge, you can put +1 here, you can put -1 there, and then you can compute subtree sums. The fact that something will have a positive subtree sum, bigger than 0, it means that there was a +1, but there wasn't a -1 yet. So if a node has positive sum in a subtree of those values +1 and -1, then the edge from this up is a bridge. And I'm sure that you can figure out more ways to do it. We can also, when we see a back edge like that, we can use heavy light decomposition to mark all those edges, to paint them with some color, or to add +1 to everything in this path. So this way we could even solve the task, let's say, almost online. You're given a tree, and you will get new and new back edges. All of them will be vertical. They will connect ancestor with descendant. After every such operation, you need to say how many bridges there are in a graph. Well, easy. I mean, easy with heavy light decomposition. You just do +1 for everything here, and then you ask how many zeros there are in the full tree. And that's doable. The kind of segment trees that are able to do it is the tree that is able to add in range, get minimum, count occurrences of minimum. And if this minimum is 0, then this will be the answer. Now let me take a look here. You should still read the article. I'm telling you some random facts, but there is a nice problem. Yeah. Here. Let's solve this one. You're given a graph and you need to direct all the edges so that the resulting graph would be strongly connected. So if you have A, B, C, D, here, can I direct edges? The cycle of size 3 is easy. I can just do it like I can make it like that, and now it's strongly connected. Everything goes into everything. But this edge, well, I will direct it in one way. What if query was just adding new edge, not always back edges? Then it would be very difficult. So let me answer this query. This task, where we just online add arbitrary edges to a graph, is difficult, but I think solvable. What you need to do is always compress cycle into one node. So when you have, let's say, a tree of big connected components, then when there is some path and you add this edge, you need to say this whole cycle gets down to a single node. And I think it can be done in linear time in total, but it's difficult. Back here. Yeah, this edge, no matter how you direct it, you will fail. And generally, when there is a bridge, you cannot solve this. When there is a bridge, you direct it in one way, and from left part of the drawing, you cannot get to the right part of the drawing. And then it turns out that just like biconnected components and bridges are related to DFS tree, we can actually create, I will copy my drawing from earlier, this thing. Maybe let's work here on this problem. Assuming that there are no bridges, then the easiest thing that you can do with this DFS tree is just direct everything down and red edges direct up. And that's it. Now you can get from anywhere to anywhere, unless there is a bridge. With green, you guaranteed that everything is reachable from the root. And now, assuming that everything is not a bridge, then there is a red edge that jumps over it, so it goes somewhere higher. Meaning from anywhere, you can go possibly down a few steps, but then you will go higher up. And eventually you will reach the root. You can treat this as an exercise to prove that this solution works, like formally. Okay. In this article, there is also part about cacti, and I strongly recommend that for ICPC, but for IOI, I think it's an overkill. I mean, graphs like this that are a little bit more complicated than trees are doable, but usually problems involving them are extremely difficult. At least what you should handle is if there is a connected graph where m is equal to n. Because this means that it's a tree with one extra edge. And that's so just a cycle with trees growing out of it. If you have this more complicated thing where cacti just, it means that every edge or every node belongs to only one cycle. So it's like a tree, but every node is possibly a cycle. And DFS tree helps a lot in implementing it, but I don't think it will happen in IOI. Do you have any questions? That's enough of random things about the DFS tree. I know it's not very organized, but there is that article, and I don't want to spend too much time, especially because many of you already know DFS tree. So instead, it's just a collection of random things, what I'm talking about today. Then there is elevator rights, and the reason why I want to talk about it is because it will be an introduction into the difficult problem. In elevator rights, there are n people who want to get to the top of a building which only has one elevator. You know the weight of each person and the maximum allowed weight in the elevator. What is the minimum number of elevator rights? N is up to 20. So we need to... It's a knapsack with multiple knapsack. So multi-knapsack problem, where all knapsacks are of the same size. Because n is up to 20, it's clearly exponential, and it smells like dynamic programming. But let's try to model this as a graph. And depending on how you model it as a graph, you will get better or worse time complexity. What is the current state? So if you have few values like 4, 8, 6, 1, and you have fit them into elevators or knapsacks of capacity 10. Then what's the easiest way to process them? Easiest meaning state cannot be complicated. And what is that state? I'm going to fit people one at a time in an elevator, and always some people will already be in, and they will fit. Now I can put them in multiple elevators, but then the state will be very complicated. Generally, remember this. Dynamic programming is very related to graphs. And that's because dynamic programming is often like Dijkstra, I would say. Dijkstra is actually kind of dynamic programming. So almost always, if it's a DP problem, you can, if you think about a state, you can say that state is a node, and you just count paths, or you find the shortest path. So here the state, either for DP or for graphs, is which people are used already, and remaining capacity of elevators, assuming that you pack people into multiple elevators. Well, this would be too slow if you fill multiple elevators at the same time, but it's better to just say, as you fill people, that they all go to the same elevator until there is no place for that and you start a new elevator. So remaining capacity of last elevator, and what else is here? Number of elevators used. From that you will get some dp. I think it's int dp of mask of people used, number count elevators used, and this int will be the remaining capacity of the last elevator, and you want to maximize that. That's one solution. In time complexity O of 2 at power n times transitions are another n. We can do better, and you will struggle to fit that into time limit. But before we optimize that, let's think about this as a graph problem. Well, if this is the state, then sure, I can say that state is, for example, 1, 0, 0, 1, and the number of elevators used is, let's say, 0. This is possible state, and from that you can use also part of the state will be what? Maybe part of the state will be the capacity, like 5. And from that you will move to another state. But can I just say that edges have lengths? So if I add a person of length 8, of weight 8, can I just say that in total I will have some path of a length or something like that? Actually, is it possible for me to just do this? I have this mask of people. Initially it's all zeros. And now I can move to this mask by using a person of length 8, of weight 8. This would be this one. So I should say maybe 6, because the third person has weight 6. Can I just create a mask of exponential size starting with 0, 0, 0, 0, and it will be very regular and boring graph, where from every binary mask there are up to n edges, each of them is of this cost. Then what will be the best cost to mask 1, 1, 1, 1? Well, both in DP and in this graph version, we can just think what happens when a new person comes. And then what is the distance? What is the value here? When we have already 3 people in, I still want to know the number of elevators, count elevators, and I want to know the remaining capacity in the last one. Remaining capacity. And an interesting observation is that I can just minimize that. Maybe it will be better to just say that here I have used capacity. I can actually find the shortest path from the beginning to the end, assuming that the distance to every state isn't just the sum of values so far, but the actual current state of the game, where the game is that we fit people into elevators. And if you have, let's say, count elevators used equal to 1, and used capacity of the last elevator, let's say it's 6, this is a value that you want to minimize. And this is a pair, and if you have another path leading to this state, and it says my count elevators is 2, used capacity is 2, then you know which one is better. This one is better. Sorry, this one is better. You want to minimize elevators. So this is better, and there is one more way you can think about it. You can think that this is actually value 1.6. I here assumed that capacity is 10. Yeah, I said fit them into elevators of capacity 10. Then I claim that this is one elevator used and 6/10 of another elevator. So I just want to run Dijkstra on real values, like that. And if, for example, distance of this mask is equal to 1.6, what it means is that I can fit those people into one full elevator and 6/10 of another. one full elevator, 6/10 or 6 divided by capacity of another used. And when I make transitions, if I consider that maybe I should now turn this bit on, I should now take this person, I need to check if this real part will fit, so whether I can just add this person. If they take capacity 3 out of 10, then here it will be good, and I will from 1.6 move to 1.9. But if I see a person of weight 5, then I cannot just say that I move to 2.1, because I cannot just partially fit this person in this elevator. No, I will move to 2.5. So if this non-integer part plus new person fits still into the same elevator, great. Just make the normal transition by increasing by this weight of this person. Otherwise, round this up to the next integer and then add the new weight. So we can just run Dijkstra on this, on real values. And the final answer will be ceiling of distance put in the full mask of ones. But of course, we don't use floating points, don't use non-integers if possible. So instead just put here int or long. First, you can use a pair, but also you can use long or int. And let's just say that, let's say capacity is 10. If somewhere you see that the distance of some mask is equal to 27, it means 2 full elevators and 7 out of 10 taken from the last elevator. So just run Dijkstra on that, starting with distance of 0 is 0. And always when you see a state like this one, iterate all bits that you can possibly turn on. And you always can do this, like current last elevator is dist of current mask modulo capacity. If last elevator plus weight of I, when you iterate I, the bit that you want to turn on, doesn't exceed capacity, then normal transition. Dist of new mask possibly becomes dist of mask plus weight of I. Else, dist of new mask becomes ceiling of that plus new weight. And what is the ceiling? It means that from 27 we would round up to, I don't know, 30, the next capacity. So it's distance of mask plus capacity minus last elevator plus weight of I. At the end, the answer is ceiling of distance of full mask divided by capacity. Do we need the graph interpretation to solve it this way? No. But graphs and dynamic, there is some relation between graphs and dynamic programming. Again, you should be aware of that. Questions? Now, I have one difficult task that I want to discuss with you. It's called bombs from ICPC. And I will give you a homework, but I don't know if we will discuss it next time or not. This is the full statement. I will give you a link later, but it boils down to this. Wait, I have a screenshot of the full thing or not? Yeah. This is the problem statement, and this is the drawing. Let me walk you through this problem. It's bomber or bombs from ICPC for some training contest. There is a grid of size 1000 by 1000 with empty cells and walls. You start in some starting cell, want to get to the target cell. You cannot pass through walls. But when you're anywhere, you can plant and explode a bomb. It will not kill you. You're invincible. But when you plant a bomb, it will destroy some area. The area is described by 2 parameters that you're given in the input, P and R. And for example, if only p is given and r is 0, then it means that we have a square. If only r is given, it means we have a diamond. Like that. Now, so you plant a bomb, all the walls in this area disappear, and you can keep moving. Then eventually you will be stuck again, or you are not stuck, but you want to use a bomb. You use the bomb, and you want to use the smallest number of bombs to get to the target. That's the problem. Now, it's not difficult to solve this in any polynomial time complexity. You can define distance of cell as number of bombs used to get here. And you can use something like BFS, I guess. So when you start from the starting cell, you start from the starting cell, you can find all the empty cells that are reachable from here. Then you can consider all possible bomb placements on the border. That's enough. And then you say everything that is within some distance, you can iterate that with for loops, mark as also reachable at distance 1. So you used one bomb to get there. Then again, you can run BFS from those cells to find empty cells that are reachable from here. Then again, plant bombs, something like that. So BFS style. That's one possibility. Second possibility, again slow but polynomial, is that you can, well, look at the grid. Always when there are two neighboring cells, they are empty, then put here an edge of length 0, but if something is blocked, then don't put an edge. There is no edge here. And also everything that is within some distance, right? So we are given a shape that is allowed. For every cell, including walls, because after doing something earlier, you might be in the wall. For every cell, create edges to everything in such area of cost 1. And again, only the border is enough, except for the target. So maybe just for safety, I will put a lot of edges, but enough would be border plus the target cell and the starting cell. And all the costs are 1. As always, you can either explicitly create this graph and store it, or you can run this 01 BFS is the name. And as you go, always when you are in a cell, just process this surrounding area. I believe that this thing can even be optimized to pass the problem. So you can implement this 01 BFS and use some smart tricks. When you are in a cell, you quickly in this area, like in amortized constant time per cell, you can get all cells that are not yet visited. For that, you will need stuff like for every column, set of unvisited cells. For every row, the same thing. For every diagonal, same thing. A lot of work, but it will work. I mean, it will give you accepted, I think. That's one possibility. Just be careful with that. So this is solution number 1. But there is solution number 2, and it's more interesting. And actually, it's very similar to elevator rides. In elevator rides, when we took another person, we had some state. And we didn't need to iterate a subset of people that we want to fit into one elevator. We took one person at a time. So here I want to implement again something like Dijkstra with some complicated state, but I want to move only to neighbors. I want to say that maybe double or something, some type of distance of cell. This will be the minimum number of bombs used going from the start to get here with some partial usage of the elevator, and here that's partial usage of the bomb. So minimum number of bombs used to get here, plus some information about usage of the current bomb, just like we did that for elevators. Elevators had capacity. Bomb has, well, radius. And now there isn't a way for you to submit this problem, bombs, but I wonder if I should tell you the full solution, or maybe it's better to leave that for next time and just leave you this as a homework, because I think it's a nice problem to come up with the solution. So let's do it this way. That's your homework, coming up with the solution. I will give you a link to the full problem statement so you can read it, and even you can implement it if you want, but you won't be able to submit. This is now the full problem link. What is more general, DP or graphs? I would say graphs. I think that almost every DP... No, not exactly that. Most DP are part of graphs, but not all of them. So 90% of the time, graphs are more general than DP. We just never think about it this way. Okay, so your homework is to finish this, and it's enough to just find a proper definition of what is distance. And you might start with here double if you want, but eventually I want you to use only integers. And some next time I will discuss the full solution here. And one more problem I want you to solve as homework, or you just think about the solution, is code versus legacy. This problem, I will give you a link in the Discord server. But I want you to solve it in better time complexity and with more difficult queries. So again, I will copy this. So homework. First, solve bombs and try to come up with an easy solution. Easy solution like elevators from CSCS. Second, code versus legacy, but first O of n log n time complexity, and second range to range edges. This is the full statement that you don't even need to look at the code forces thing. That being said, again, I'm pasting a link for you, and I will summarize that in Discord server for what you need to do. So there are n nodes numbered from 1 to n, m available teleports. Each teleport is described by 5 elements, meaning from range AB to range CD, you can jump with cost. Starting from node 1, compute minimum possible cost to get to each node, which means run Dijkstra, but edges are more complicated. Code forces problem can be solved in time complexity that is slightly worse than this, and it only has more limited edges or teleports. Next time we will discuss this with those challenges, and we will discuss bombs. Do you have any questions? If not, then thank you for listening and have a nice day off. Today will be off, solve homework if you want. We see each other in 2 days, and I think we will do Polish Olympiad 2021. Unless there are some technical issues or something like that, then we'll switch to something older. Thank you all. I will give you in Discord server the registration link from Huawei. Please fill it. If you don't do it in 2 days, you will be kicked out from the server. You also need to provide your Discord handle there. Or we'll do something like, I don't know, we will take away all your roles, the camp participant role, and you get a role back when you fill the form. Sorry about the inconvenience. Okay, have a good day. Bye bye.